last year we had, supplies that we needed to take. So what happened was that I was traveling through Nairobi to Arusha and catching the flight there. But because my flight was a little bit late, they figured this guy is not going to show up anymore. So they offloaded my luggage, and my luggage was this whole box of workshop supplies. Now, the people in Arusha didn't want to give my box of workshop supplies back. Because I don't really know what they wanted. I think they wanted some money. So the day before DSA started, I just took a cab to the airport, walked straight into the arrivals hall, passed a baffled security guard who was standing there like, "What are you going to do?" I'm like, "Yeah, I'm just going to retrieve some luggage." And in there I saw, in the baggage hall, I saw my box. I just figured, well, fuck it. I just took my box, walked out, no one stopped me. So this time I took everything as hand luggage. It's really big. So we got everything. Still a day late, but here we are. So data science. Like every time I talk to a data scientist, they're really focused on what's happening inside that model. What regression algorithm do you need to use? What reward function do we need? Do we need to put it on a blockchain or not? So really focus on that. And for me, it's kind of what I was very happy about when I was here last year is the moment that we actually step outside of that. We step outside of our actual models and we start looking at what do we want to achieve with this data, or how do we get this data. So one of the guys here actually at the university here in Kenya, he was repurposing the hardware that we developed last year during DSA to actually make a device to do water metering. And I thought that is awesome, step out of your comfort zone and start hanging over the water, latching onto a pole to actually start reading this information. I think that is fantastic. That's why I'm very happy to be here and today and talk to you and actually do some actual field work 3 days in a row. We're actually going out, we're going to a greenhouse, we're going to a conservatory, and we're going actually into the jungle to set up some camera traps. I think this is awesome. I mean, for me, walking out into the field, it's kind of weird. I mean, yesterday we were walking for 10 kilometers all day, back and forth through the greenhouse. And it's like, fuck, I became a software engineer, so I could just sit behind my desk all day and just type. But the stuff is going to be cool if we're going to have a couple of sensors actually deployed, and the whole idea is that we're going to leave this behind and keep it running for a while and have people do something with this data. That is so much more powerful because all of a sudden we've created something that wasn't there before. It's not some data set you can download from some website. It's something that we're actually building together here and setting up here. I think that's awesome. So yeah, this session is called Fundamentals of IoT. So for me, Internet of Things is adding digital inputs and outputs to physical things. It's kind of yes. Okay, sorry. So yeah, my name is Jongboom. I was trying to do that here's the box of DSA, but I got sidetracked a little bit. My name is Jongboom. I'm from the Netherlands originally. I work for ARM. ARM is a semiconductor company. We develop very low power and very efficient computer chips. Something we're actually going to be doing here. And I run a very small team of developer evangelists, which is kind of a weird title. My dad was an actual evangelist, so I'm kind of stepping into his footsteps. But what we're doing is we try to make people enthusiastic about technology, preferably our technology. But we do it from a technical background. So everyone on my team is an actual developer. We still spend 50% of our time hacking on stuff that we think is really interesting, hopefully incorporating our tech, and then going out and talking to people or running workshops. So yeah, last year Damon sitting there, so used to be a lead data scientist in ARM, who dragged me into the fields in Africa. I was running behind cows with stuff, and then I realized this is the real work. This is awesome. Does that answer your question? Cool. Yeah, so Internet of Things, digital inputs or outputs of physical things. So that can be very simple things that are already kind of digital, like a lamp. It's the field of view light. Just can put colors on it, it's very nice. It can be stuff where we just want to get some basic information or something, relatively static information from living things, like putting a plant monitor. So that's something we're actually going to be building today. Or you can take it even a step further and add digital inputs and outputs on things where it just sounds very wrong, like what we did last year at DSA by putting the Fitbit for cows, the cow tracker, on here. Who was at the field work? Just a couple people. Okay, this was hilarious. So the whole idea was that we wanted to make a sensor where we could have some information about what is the cow doing, and then trying to analyze that, throw it through a machine learning model, and see if the cow's pattern of behavior would change when it was getting sick or when it was in heat, because apparently sperm samples are really expensive. So we did that, and they basically held the cow for us in a really confined space for about an hour while the farmer and the vet were explaining. And we didn't realize that, well, if a cow is just standing like this for an hour in a very confined space, it gets really anxious. So we put the sensor around the cow in the moment that we figured, well, okay, now let's record some data. Mike was actually, writing down what the cow was actually doing, and we were recording the sensor data. At that point, the cow was like, yeah, I'm free, and it just ran off. So it was Mike with his notepad running behind the cow. It was me with my laptop, someone else with a Wi-Fi base station. But it's interesting, if we can gather this data from living things, we could do some really interesting stuff with that. For example, predict when a cow gets sick based on this data. There's two approaches that I see for Internet of Things. We can just look at the normal data collection flow, where the device that we're having is just a very simple data gathering device. It has a sensor, just gathers some data and then sends it off to some cloud where you actually do the compute or the machine learning. But we could also say, well, we want to add some compute on the edge or ML on the edge and actually run a machine learning algorithm directly on the device and then only send the conclusions over. For me, it both feels a bit Internet of Things. I mean, data is kind of, vast amount of data are kind of useless if it's just data. Then it sits in an Excel sheet or a CSV file or somewhere in a database. But only if we throw some machine learning at it, then all of a sudden we can actually make sense of this data. So that's why I think that DSA and IoT are a really nice fit. So what do we need if we want to build a device like this? So we need a sensor, something where it sense. So that can be the soil moisture for a plant, or it can be a temperature sensor so we can detect the skin temperature of a cow, see if it changes. We need a little computer device. Even if we don't do compute or ML on the edge, we still need a little computer device to actually gather this data. And then present it in some form, and then some connectivity. So send it actually over. Preferably we want a computer that's very cheap, so we can put a lot of them in the field. And it's not that bad if someone steals one. Low power preferred as well. So if I'm going to put a sensor in a greenhouse and I'm going to tell the staff that every 2 days they need to go into the greenhouse and change the batteries, this project is going to die pretty quickly. So we want to have something that can actually run for a couple of months. And then we want connectivity that is preferably also relatively low power, but also long range. So if I have an IoT system in a greenhouse and I need to put a Wi-Fi base station at every greenhouse, it's not going to fly because we don't even have power next to the greenhouse. So let's go to the cheap and low power computers first. If you're thinking about starting with Internet of Things, if you're doing like an IoT 0 to 1 tutorial, very often you run into something like a Raspberry Pi. It's really nice prototyping hardware. The downside is it's not very cheap, as in $30 or something, and it's also very not low power. Like running anything on a Raspberry Pi will drain even like a nice power bank in a day or two. However, if you need the compute power, that is your only option. We're going to do camera trap work on Saturday, and running both the camera plus the ML algorithm all on the edge to detect what we're seeing, you need all this compute power. The downside is we can't really run out of battery in that case. For a lot of other sensors, like soil moisture, temperature, etc., we don't really need all that compute. The only thing we need is just read a sensor every minute and send some data over. So for that, you don't really want to use a computer like a Raspberry Pi or something that runs Linux. You want to run on a microcontroller. So microcontrollers are really ubiquitous around the world. So last year, ARM sold about 15 billion microcontrollers with a B, which is a lot. Every time you see a smart device, even something that doesn't look smart, like the beamer here, the projector, has one of these inside. So this is a Nest, like the self-learning thermostat. I thought it's kind of nice on an ML conference. So this little piece here is less than a square centimeter. That's the brains of this whole thermostat, and it's a microcontroller. So these are really cheap. They're about $1 each. They're slow. This is like if you're using your computer from the 1990s, but then with even less RAM. So the device that we're having here today, that we're going to build something with, has 128 kilobytes of RAM, so very constrained. But the nice thing is that it's really low power. If you put it in sleep mode and then run it off the three AAA batteries, you can run it for 10 years. It's really cool. Of course, every time you do something with it, you dive into that power budget. But it's really efficient, cheap, and small, which is really nice for Internet of Things stuff. That's kind of the reason why ARM, or why we're doing something in my division here, is that like the very basic stuff that we're also going to do today is very easy to get right. You know, you hook up a couple sensors, you write a little bit of code to read that sensor. And then we also see that, however, if you're going to do 1,000 devices or 10,000 devices, maybe 100,000 devices one day, all of a sudden there's all this stuff that you also need to take into account. What if my device gets hacked by someone or gets attacked by someone? What if I have made a mistake somewhere in my code and I want to update all of these devices? I can't really go into the field, retrieve all of them, put a new firmware on, and fix it that way. Which can be really shit, because if you realize I just deployed 10,000 devices all around Kenya, and I have a bug where they're going to run out of power within a month, then you better have a way of actually fixing that. So within ARM, we're building a software platform, we're using it today, that makes it easier for these constrained devices to deal with this kind of problems. Firmware updates, making sure that they're secure. These ones have a little bit of storage, so if there's no connection, you can just store this data on there. Need some drivers for that. And we're doing that with the Mbed platform. So it's an open source project on the Apache 2 Foundation. We have 300,000 developers and about 150 development boards. One of these development boards we're using today. That's kindly donated to you by ST. ST. And with the connectivity, and that's important here, because depending on your device, you want some short-range connectivity, you want some long-range connectivity, you need high power, low power. So we got all supported. That's why we're using this today. What I'm kind of proud of is that it's really open source and community built. We have 325,000 developers on here. So, and they publish libraries for all kinds of stuff. So I bought these temperature humidity sensors. I go to a website, I type like the type number, and someone already wrote the code for me. I thought, that's nice, that saves me a lot of time. So we have over 400 people actually contributing to the project, which I think is really nice. So as I said, a microcontroller is really small, like a square centimeter, but I'm not gonna ask you all to solder on this very small piece of silicon these sensors. So for that we have a development board. So that's, actually, I'm just gonna throw everything out here. So it's this one. It's still not very big. The brains is literally here. It's the little piece on here. And then to make it easier to attach new sensors, there is general purpose input-output ports. There's, I think, like 50 of them or something here. And you can just like plug new peripherals in. Very nice. So if you're, I did put it in. So if we want to put a moisture sensor, for example, so the moisture sensor that we have here has 3 wires coming out. So it has a power wire, there's a ground wire, so that's just make sure that some electricity is flowing, and then there's a signal pin. And the signal, in this case, is an analog pin, so depending on like how moist the soil is, the resistance will go up or down. So we connect it to an analog pin on this board. So there's an analog pin here, so we can just plug it in there. So there's like a little picture of this development board telling you exactly which pin is what. The other one's to power and ground, and then we have this connected to the dev board. And after that, reading this value, like seeing how moist stuff is at that point, is very straightforward. You just declare it. I say I have a variable moisture. It's connected to pin A3, my analog pin, where I connected it physically. It's an analog value. I can read this and then print it out or send it over the internet or do something with it. So very straightforward. What is nice, I think, here is that if you say wait, it just automatically puts the device to sleep. So we don't consume any power if we're just waiting. So that makes it really nice to make energy efficient stuff. All right, so we got 15 minutes before our break. So let's go to the next one. So we got the device basically covered here. I would also really like a low power, long range network. So because I want to get the data from 10 of these devices in the greenhouse, and I'm going to get them from the conservatory, preferably without changing the battery, with a little bit of range. Up until a couple of years ago, this was kind of the landscape. We had, if you want to go really low power and really close, you have NFC, like the stuff that you use to pay. I think with M-Pesa you can do it as well. It's like you beep against someone else and now you pay it. You got Bluetooth low energy, the stuff that you use for your Fitbit or for your heart rate monitor. Wi-Fi, which we all know and love, but breaks every now and then. But it's very short range. The moment that I walk 100 meters, I don't have any range anymore, and it's also relatively high power. And then it's the cellular technologies, which are very long range, that it works everywhere, but also very high power. Your phone is going to run out in a week, even if you're not using it, by just being connected. But for us, like the sweet spot in IoT is kind of here. We need long range and low power. And the bandwidth doesn't really matter. If all I'm sending is some moisture values, some soil moisture values, I don't really give a shit. So this is where a technology popped up, LoRaWAN. Who's heard of this? Wow. Okay, cool. Then I can do like a nice introduction here. So LoRaWAN is what its promises is about 10 kilometers of range, if configured properly, and 10 years of battery life. We have some photos of our experiments that we did yesterday with placing base stations. So it's a really nice fit. It also comes with very, very low data rate. So basically what you can send over is maybe 20 bytes a minute or something. But it comes with very low power, very long range, which is really nice. Yeah, so stuff where you can use it for, stuff like, is a car parked here, yes or no? It's B&I, they bake something into concrete, and then they use the changes in the magnetic field above the sensor to detect if there's a car or not. It's kind of clever. Stuff in a shipping seal, which you put inside a shipping container, just says the seal has been broken or not broken. Or I hang something on an electricity pole, and whenever the pole goes down, it gives me a signal and say, hey, this shut-off broke. So very simple sensor values. You can't stream video over this. Or in very low resolution. But what you could do, you could inspire it with ML on the edge. You could say, well, I run my camera trap, and then I send a conclusion, like, hey, I saw an elephant, or a set of features. You run an autoencoder, and you compress this down, and you just send that over. That's something you can actually do, not raw data. Okay, so how does it get these kind of, why does it have these things? Yeah, here we go. Why can I go 10 kilometers of range if my Wi-Fi boils down after 100 meters, and why can it run for 10 years on a battery if my phone dies after a week? Do we have people here that do like RF stuff for the daily life? Long time ago. Okay, so if we have a signal that goes from A to B, so we have on one end, we have a transmitter, and on the end have a receiver. If you want to know if this message is going to make it from the transmitter to the receiver, we have a couple of variables. The first variable is how much power do we put into the signal? So how much milliwatts of power? So in the case of the device that we're using today, it's only 25 milliwatts, which is very little. It's a lot less than you put through a mobile phone. Then we lose a little bit because we've got connectors, and we gain a little bit because the antenna, we don't need to send out in every direction. We want to send out mostly in the horizontal plane, so we have a little bit of gain there. Then there's a lot of path loss, so we encounter buildings. We're also fading. The signal just gets weaker the further it goes. And then on the other end, we put some power into the receiver, and then hopefully it picks it up. Now, whether it picks it up depends on the receiver sensitivity. So you see that we lose power here all the time. And the receiver sensitivity is a number. Just like the 25 milliwatts transforms to 14 dBm, logarithmic scale, the receiver sensitivity also has a dBm figure. In case of LoRa, the receiver sensitivity is 137 dBm below. And then the difference between the amount of power we put in and the receiver sensitivity, that's our link budget. That's how much signal we can lose along the way. So 151 dBm is quite a lot. Let's say I want to go through a concrete wall, that's 20 dBm. So we can go through 6 concrete walls, basically, and still have a signal. That kind of helps us here. So if you're looking at comparison, for example, with Wi-Fi, Wi-Fi uses a bit more power, but the receiver sensitivity is a lot worse. So it gives us a 90 dBm link budget. You might think, well, 90 dBm versus 150 dBm, it's like twice as much, who gives a shit? But because it's a logarithmic scale, every 6 dBm extra, you basically double your distance. So this is not tens as much, it's 2 to the 10 times as much. So you see it if you're looking at the theoretical maximum in free space, if we all be living somewhere near the moon, is on Wi-Fi about 550 meters, the absolute theoretical maximum that a Wi-Fi signal can travel. Whereas for LoRa, the theoretical maximum is 850 kilometers. Fucking awesome. So to actually prove that, a couple of guys in Amsterdam from a startup called the Things Network, they decided to do a little experiment. So they loaded one of the devices, very similar ones that we have today, up into a weather balloon, let it go up, and then tried to like measure the distance that it went, and they actually managed to get over 700 kilometers of range. It's like, really cool. The downside is that we don't live in free space. So as said, there's attenuation, there's buildings that block stuff, there's even a window blocks stuff. There's reflection and diffraction. So a signal, let's say that I have a signal here and a signal here and I got a big building in the middle. It can't go straight through, but it might find a way by bouncing off other buildings, which can be a really good thing because I might be able to reach the receiver that way in a way that I couldn't do otherwise. It can also be a very bad thing because I have 2 waves and one is bounced off, it goes the other way around, it can actually diffuse the signal. It's kind of annoying. And then the last thing, which you're going to find out if you have both the transmitter and receiver very close to ground, is that if you have a very big mass, kind of in a little zone, a little oval that you can draw between these two, between the transmitter and the receiver, is that you have the Fresnel zone. And if the Earth is in the Fresnel zone, which is a really big mass, you're going to lose a lot of signal. So we saw that actually yesterday. We had a gateway on the bottom floor, and then walked to and then had a transmitter also basically at ground level. We got like 100 meters in range, and then we put it on the 3rd floor, and all of a sudden we got a kilometer. And that's just because we don't have the Fresnel zone, we don't have the Earth in the Fresnel zone in that way. So putting your transmitter as high as possible is always a really good thing. This was our test setup yesterday. This was one of the buildings. So we couldn't really find a way of like mounting our gateway on the roof. So we dangled it outside of a window. we just taped the wires against the window and just like hang it outside. That worked surprisingly well, just not good enough. I mean, what you can see here already is that the structure of the building is already kind of all around it. So typically if you want to place a gateway not on the roof, but rather against the wall, you need like 50 centimeters away from the wall to get like best signal. And even here we only managed to get like a kilometer, which is kind of cool, kind of fine, but it's not 700 kilometers.
Is the area, why the area would it have been better if it was pointing upwards? So
yeah.
Like, never mind.
Yeah, it should, because now the gain is a little bit, the gain is a bit wrong. Yeah. Yeah, correct. Yeah. Yeah, correct. Well, so we hang this on the building next door, and we almost managed to reach the greenhouse. I think it's 1.2 kilometers away. We were like 100 meters short, so it's kind of sad. So we had to relocate this gateway there. So theoretical maximum and actual stuff that happens not completely true. This is also kind of bad gateway placement. In this case, the gateway is placed inside, so you have the window there, but you also have like some iron, bars. I don't know. It feels a bit like a prison. In between, so that's also going to block quite a lot. So suboptimal antenna placement has a really deteriorating effect. There's been a couple of guys that have been doing like proper modeling of cities and then mapping the signal that you can expect, or like the signal strength that you can expect here. So this is based on Tokyo. So we see in a large city with a transmitter on 10 centimeters high and a receiver at 40 meters high, properly on a roof, so not mounted against the wall. would expect about 4 kilometers of range. If your speed goes up, so you need higher speed, then we go down quite a bit to 2.5 kilometers. That's because your receiver sensitivity goes down. And at a suburb, so let's say that we managed to put our gateway antenna on the big tower, the radio tower that we have outside of the university here, about 100 meters high. I'm pretty sure that we could go 13 kilometers through that, which is pretty nice. Apparently Nyeri is very small, so we could reach all of the town basically that way. So I'm pretty sure that if we have 2 or 3 gateways placed all around Nyeri, we could cover the whole city and get pretty good reception there. If you're more interested in like how this actually works from a physics point of view, there's a video. I have the slides online at a later point. But it actually explains like where. So what's cool about LoRa is that it can detect signals under the noise floor. So where we, as humans, only see noise, it can still detect that signal, and that's because it's using, so it's using a technique where it's basically sweeping from one frequency to another over a straight line. So even if it gets intercepted by other technology, you can still follow that sweep, and that's how you can decode it. So someone made a really cool video about doing this. Given that we're basically at half an hour, like 4 minutes left, I don't really want to dive into the next section yet. If we can do a coffee break right now, then we can drink coffee, think about all of this, think about how awesome the stuff is that we're going to do in the field, and then come back and do that. Sound right? Damon?
Take more questions and I'll ask the first question.
Okay.
What is the fieldwork we're doing today?
So, what is the fieldwork at? Yeah, so I had it actually in the last couple of slides. But yeah, this afternoon we're going to go to the greenhouse. So there's 2 greenhouses being located about 1.2 kilometers away from here. In there we're going to place a couple of sensors. So we have temperature and humidity, and we got soil moisture. So we're going to put 5 of them in each greenhouse. So they're going to be connected to the base station that you saw dangling out of the window, only now located a little bit closer to the greenhouse. And they're going to be sampling data every 20 seconds, sending the data in, and then we'll create a nice data set. And the idea is that both of these greenhouses are places where we grow tomatoes, or tomatoes, as Damon says. He's from South Africa. And the idea would be that after, when the next harvest is, that we could see which greenhouse yields the most tomatoes, and see if we can actually find the correlation in the data based on like humidity, temperature, soil moisture, etc. from that. That will be an open data set that we're actually building today. Yes?
Yes. So I understand the company released some sort of simulator.
Yeah.
So how far can one go with the simulator? Can you use it in the field or it's just on the computer?
The simulator, yeah. The simulator can go as far as you have internet, but yeah, you can't really get real data because it's a simulator.
Does it have all the sensors?
It has the temperature and humidity sensor. So we'll actually be using that to quickly mock some stuff up later at practical work. Just so you can try some stuff out a lot quicker than you can do on an actual device. But yeah, we'll be using that. Yeah.
I hope it's not a silly one. The sensors.
Yeah.
Actually, there's a specific one for humidity and another one for temperature.
Yeah.
So the designs are based on what you're going to do for.
Yeah, so I mean the major design decision that I took when buying these ones are they available to ship today, so we can actually get them, and are they easy to hook up? So these are relatively cheap ones. If we decide, like Mike is using $70,000 sensors, $7,000 sensors in his work around monitoring air quality. Yeah. So these ones are like $7 instead of 7,000. So there's like a wide variety in like what you need and what specifications you need. So for example, the temperature ones are like half a degree accurate only, which is, if we need higher precision, then we can get something else.
So
yeah.
Did you say you can only send about 20 kilobytes per minute?
20 bytes.
20 bytes.
Yeah. Yeah.
So what is the resolution of the measurement?
Of the temp.
Say the humidity?
I think the humidity is 2% or something. I can look at the data sheet.
So how many
Oh, I'm compressing it down in 2 bytes.
2 bytes.
Yeah. So just the value. So it's exactly
We're
1030.
measuring it every
Yeah.
20 seconds, is that what you said?
That's what we're doing for now.
5 measurements per minute, 10 bytes. So we still have a few bytes left over.
Well, so we had soil moisture. So yeah, so the thing is like 6 bytes per cent. So we're using 18 bytes. There's a little bit of slack. I mean, it's not like a hard science, but it's kind of what we can do. It also depends like how many devices do you have in the field. If you have 1,000 devices in the field, you want to send a little bit less to avoid collisions. But with the 20, 30, 50 devices that we're deploying in the next couple of days, doesn't really matter.
Well, I guess that raises the question also of compression.
Yeah.
And error correction.
Yeah. So right now, don't do any error correction. Just best effort. If it makes it through, it makes it through. If not, it's fine too.
Does it have error
Hmm?
detection? Does it have error detection?
No.
I guess we'll find out with your.
Well, yeah. I mean, so we're going to come back to that. But the idea is just there's no communication back at the moment between the base station and the device, just to save power and whatever. So the device just broadcasts it out. Hopefully, the gateway picks it up, and if we miss a couple of frames, we miss a couple of frames. It's in this case, it's not like highly critical data. If it's stuff like, oh, my alarm goes off and I need a guaranteed link at this point, you might be either better using a different technology or you need to use acknowledgements, basically where the gateway says, hey, yeah, I received it. Here's my acknowledgement.
I mean more error detection, so if a bit gets clipped, does it?
Like that. I mean, there's a CRC hash on it. So, plus everything is encrypted. So the moment that a bit flips, then you can't decrypt it with the keys anymore. So there's no risk in that kind of errors in the data. Coffee. Sounds good? All right, cool. See you in 30 minutes or something. Woo! It's great.